welcome to the deep dive. You sent over some really fascinating material, this whole chapter on cleaning aircraft and maybe more importantly, controlling corrosion. I have to admit, when I first saw aircraft cleaning, I thought, well, how complicated can that be? But wow, digging in, it's so clear this is absolutely foundational stuff.
Absolutely. It might seem, a bit niche, but think about the forces involved.
Yeah.
The stresses on an aircraft. The integrity of the materials is just paramount. Preventing and dealing with corrosion, it's this constant, really meticulous effort. It's a great example of how seriously aviation takes even the seemingly small details.
Right. It's not just about looking good.
Not at all. It's about making sure the aircraft can do its job safely, flight after flight after flight.
And it's interesting. It's not like we've just engineered this problem away with modern materials, right? Even with composites, there are still tons of metal parts.
Oh, definitely. Essential structural components, fasteners, systems.
Yeah.
Metal is still everywhere.
So, okay, our mission for this deep dive. Let's really pull out the key knowledge about aircraft corrosion for everyone listening. Why does it matter so much, and what are the big takeaways here?
Right. Let's start with the basics. What is corrosion? At its heart, it's just the deterioration of metal. It's a electrochemical attack. Your sources had a good analogy like wood rot. It's this gradual weakening, this breakdown, and it's not just surface deep. It can go right into the structure.
Like wood rot. Okay.
Yeah.
And the main culprit seems pretty simple. Water, especially salty water, plus oxygen from the air.
That's the fundamental recipe, yes. Water, or even just water vapor, especially if it has salt dissolved in it, combined with atmospheric oxygen. And like you said, the sources point out aircraft operating near the sea or in areas with lots of industrial fumes. Much higher risk. Those environments really accelerate the process.
And the potential consequence, if you don't catch it, is, well, it's stark. Structural failure.
Exactly. Which is why it's taken so incredibly seriously.
Okay, so the material also gets into how corrosion actually looks on different metals, which seems super useful for, spotting it early.
It is. Very important. For aluminum and magnesium, you're looking for pitting, sort of edging on the surface, often with a gray or white powdery deposit. Copper alloys, they get that greenish film we often see. And steel, of course, gives you rust, that reddish stuff.
Rust, yeah. Everyone knows that one.
But the key thing is, even after you clean off that surface deposit, you might find the metal underneath is still etched or pitted.
And those little pits, even if they look tiny, they can be a big deal. The chapter highlighted that they can become starting points for cracks, especially under stress.
Precisely. A seemingly small pit can act as a stress concentrator. It's a weak point where a crack can initiate and then propagate, potentially leading to a much bigger structural issue.
And some corrosion is particularly insidious because it can actually creep under the paint or other coatings, spreading unseen until it causes blister or worse. Wow. Okay. So it's not just a surface check. We need to understand the factors that actually sort of fuel the attack. Your chapter had a pretty long list.
It did. And it covers a lot of ground. Everything from the type of metal itself. Some are just naturally more reactive, more active than others. Pure metals versus alloys. Even the boundaries between the tiny crystals, the grains in an alloy. How the metal was manufactured matters too. Heat treatment, the direction the grains are aligned in. That can all influence its susceptibility.
And then there's the classic one, different metals touching each other. Galvanic corrosion.
That's a big one, yes.
Yeah.
Galvanic corrosion. You get two dissimilar metals in contact, add an electrolyte like rainwater with some salt in it, and boom, you've essentially created a little battery. The less noble metal acts as the anode, the negative terminal, and it corrodes preferentially.
So it sacrifices itself, basically.
In a way, yes. And the relative surface areas are critical. If you have a small area of the corroding metal touching a large area of the more noble metal, that corrosion can be really fast and severe. All that energy focused on a small spot.
Okay, that makes sense. The list kept going, though. Temperature, electrolytes like hard water or battery fluids, just the amount of oxygen around?
Yep. Temperature speeds up most chemical reactions, including corrosion, so hot, humid climates are worse. Electrolytes provide the pathway for the electrical current in electrochemical attack. Oxygen is usually needed for the reaction. And it's interesting, even tiny biological organisms, slimes, molds, fungi, they can contribute by trapping moisture against the metal.
Really? Like little moisture traps?
Exactly, creating these damp pockets. Then there's mechanical stress, which can lead to a specific failure mode called stress corrosion cracking. And of course, just time. The longer the exposure, the more chance for corrosion.
I was genuinely surprised to see pencil marks on the list. Lead or graphite.
Yeah, seems minor, doesn't it?
Yeah.
But both lead and graphite are conductive. They can actually set up tiny galvanic cells on certain metals, especially aluminum alloys, and kick off corrosion. So best practice is to avoid marking directly on the metal.
Good tip. And the impact of where the aircraft operates, the climate, that seems huge. The chapter mentioned mild, moderate, severe zones with different inspection schedules.
Absolutely. High humidity, salt spray near coasts, industrial pollution. These create much more aggressive environments. The suggested intervals, like 90 days for mild down to maybe 15 days for severe, really show how much more vigilance is needed.
And then there are the factors we have more control over, like just letting dirt or oil or salt spray sit on the plane.
Exactly. Basic housekeeping, really. Foreign material like soil, dust, oil, saltwater residue, battery acid, even welding flux left behind from repairs. All that stuff needs to be cleaned off promptly. And even internal stresses left in the metal from how it was manufactured can make it more vulnerable later on. So meticulous cleaning is just your fundamental first line of defense.
Okay, so we know what it is, what fuels it. Let's get into the actual mechanisms. The chapter talked about two main types, direct chemical attack and electrochemical attack.
Right. Both end up converting the metal into some kind of metallic compound, like an oxide or a salt, but they get there differently. Direct chemical attack is more, well, direct. A corrosive liquid or gas just reacts straight with the metal surface. The spots where the metal breaks down, the anode, and where the corresponding reaction happens, the cathode, are at the same point.
Like spilling battery acid?
Exactly. Spilled battery acid or fumes from it. Those welding flux residues we mentioned are a big one. They could be very corrosive. Even caustic cleaning solutions if they get trapped or aren't rinsed off properly.
It's good that modern sealed batteries reduce the big spill risk, but sounds like flux and cleaners still need careful handling.
Oh, absolutely. Flux residues often absorb moisture from the air. They're hygroscopic, so they can just keep corroding over time, causing nasty pitting if they aren't removed completely. And yeah, strong cleaning solutions need to be managed carefully.
Okay, then the other one, electrochemical attack. That sounds more like the battery analogy again.
It is. It's very similar to how electroplating works, or a dry cell battery, and it needs four things to happen all at once. You need an anode that's the metal that corrodes. You need a cathode, a dissimilar conductive material nearby. You need an electrolyte that's the conductive liquid, usually water with impurities. And you need electrical contact between the anode and cathode.
So if you break that circuit, stop any one of those four things.
You stop the corrosion. Exactly.
So even just a tiny scratch in the paint, exposing bare metal, that could be the anode. If there's another bit of metal nearby, maybe a fastener acting as the cathode, and some moisture gets in.
Perfect example. That completes the circuit. And as the source material notes, paint can actually hide this in the early stages. You don't see it until the corrosion products start building up. They actually take up more space, more volume than the original metal. That expansion is what causes paint to blister and flake off.
Ah, okay. The chapter also said even on one piece of metal, tiny differences in electrical potential can create these little local corrosion cells.
That's right. It's fascinating. You don't even necessarily need two different types of metal. Differences in grain structure, surface contaminants, even just variations in oxygen availability across the surface, if there's an electrolyte present, can create tiny anodes and cathodes on the same piece of metal. This is where the idea of a metal's nobility comes in its tendency to give up electrons. Less noble metals corrode easier. And within an alloy, the different metallic components can have slightly different potentials, setting up these microcells.
So how do you fight that?
Well, the key principle is regular cleaning, removing the electrolyte and maintaining the protective finish. The paint or coating acts as a barrier, breaking that electrical circuit. That's the foundation of effective control.
Okay, mechanisms covered. Now, the different ways corrosion shows up the many faces, as the chapter called it, sounds like there are quite a few distinct looks.
There are. The most common is probably surface corrosion, sometimes called uniform etch or attack. To general roughening, maybe a frosted look. Pitting, that powdery deposit we talked about, can be chemical or electrochemical. And always look out for paint blistering, often a sign of this happening underneath.
Then there's filiform corrosion. That sounds weirdly biological, worm-like traces.
It does look strange, like tiny threads spreading under the paint. It's a specific type, an oxygen concentration cell, that happens under organic coatings, especially polyurethanes, it seems. It needs high humidity, maybe 78 to 90%, and a slightly acidic surface to get started. Interestingly, on steel, the threads don't tend to cross, but on aluminum, they can spread out more and cause deeper damage. If left unchecked, it can lead to intergranular corrosion too.
How do you stop that?
Prevention is key. Controlling humidity, using coatings that don't let moisture through easily, and washing the aircraft regularly to get rid of surface contaminants. If you find it, you generally have to remove it mechanically, like blasting or sanding off the affected coating and corrosion.
Pitting corrosion sounds particularly nasty. Highly destructive, the chapter said.
It is. Very common on metals that form a protective oxide film, like aluminum and magnesium. It starts often as just that white or gray powder, but underneath you find these tiny, deep holes or pits. The real danger is the damage can be way out of proportion to what you see on the surface. A few small pits could hide significant weakening.
And dissimilar metal corrosion, galvanic, we touched on that, where different metals meet with moisture if the insulation fails.
Yep. Can be hidden, can be serious. And it's not just design contacts. Your source wisely points out using steel wool or steel brushes on aluminum or magnesium is a bad idea. Tiny steel particles get embedded, create galvanic cells. Same risk with some abrasive pads if you're not careful about cross-contamination.
Right. Then there was concentration cell corrosion, several types under that heading.
Yes, it's all about differences in the local environment. Metal ion concentration cells happen in stagnant areas, like between clamped plates, fang surfaces. Where the metal ion concentration builds up, it becomes cathodic. The areas next to it with lower concentration become anodic and corrode. Oxygen concentration cells are the opposite, sort of. Areas with less oxygen under gaskets, wood, rubber, trapped debris become anodic and corrode. Stainless steel can be quite susceptible to this, and active-passive cells occur on metals that form a protective passive film, like stainless steel or aluminum. If that film gets broken locally, say by a scratch or under dirt, the small exposed active area corrodes very rapidly compared to the large surrounding passive area. Leads to pitting.
Intergranular corrosion. That sounds really sneaky because it attacks along the grain boundaries inside the metal.
It is insidious, caused by variations in the alloy structure, often related to heat treatment. Some high-strength aluminum alloys, certain stainless steels are prone. The big problem is you can have significant damage happening internally with almost no sign on the surface.
And exfoliation is like an advanced stage of that, where the surface layers actually start lifting off.
Exactly. The corrosion products build up along those grain boundaries just below the surface, and the pressure pries the layers of metal apart. Looks like puff pastry almost, often seen in extruded parts like stringers or spars. Hard to spot early.
Stress corrosion cracking. The combination of stress and a corrosive environment sounds like a recipe for disaster.
It's a major concern. The stress can be residual from manufacturing or applied in service, like from fasteners or loads. It doesn't necessarily need super high stress. Failures can happen well below the yield strength. Specific alloy environment combos are known culprits. Saltwater on high-strength steels or aluminum alloys, for example. Prevention involves coatings, stress relief treatments, inhibitors controlling the environment, even shot peening to create compressive surface stress.
And fatigue corrosion, that's cyclic stress plus corrosion.
Right. The corrosion basically weakens the surface, creates pits or notches that act as stress risers, making it much easier for fatigue cracks to start and grow under cyclic loading. It significantly lowers the stress level needed to cause a fatigue failure. Very dangerous.
Fretting corrosion, that's the one with the smoking rivets? Damage where parts rub slightly?
That's the one. Tightly fitting surfaces with just a tiny bit of relative movement. You get pitting and this fine, often dark-colored debris, hence the smoking look around rivet heads sometimes. Interestingly, it's not usually driven by an electrolyte. Moisture might even slow it down in some cases.
And galvanic corrosion gets another mention at the end there, just to really hammer home the point about dissimilar metals.
Yeah, it's fundamental. Two different metals, electrical contact and an electrolyte. The rate depends on how far apart they are in the electrochemical series, their activity difference, and critically, the relative areas. Small anode, large cathode, very rapid corrosion of the small part.
Okay, loads of different types. What are the actual agents, the common stuff aircraft run into that causes all this?
Good question. The chapter breaks them down nicely. Acids are generally bad news for most airframe alloys. Think sulfuric acid from batteries, halogen acids, even things like nitrous oxides from pollution, or organic acids from waste products. Alkalis are generally less aggressive than acids, but aluminum and magnesium are very susceptible unless the alkali solution has inhibitors mixed in. Things like washing soda, potash, lime. Ammonia is also specifically mentioned as corrosive to aluminum. Salts, as we've discussed, are prime electrolytes when dissolved in water. They really promote electrochemical attack on most metals, though some stainless steels hold up better.
And then just the air and water themselves.
Absolutely. Oxygen and moisture are the big atmospheric players. Add salt spray near the coast or industrial pollutants, and it gets much worse. Water itself varies. Dissolved minerals, impurities, dissolved oxygen, its conductivity all play a role. Even temperature and flow rate matter.
Right. Given all this, it's crystal clear why preventive maintenance is so vital, even with better materials these days.
Totally. You can't get complacent. Consistent, thorough preventive maintenance is the absolute cornerstone. And your source rightly mentions always checking the safety data sheet, the SDS, for any chemicals used. Know what you're handling.
The chapter lists out the functions. It's quite a list. Adequate cleaning, thorough lubrication, detailed inspection, prompt treatment, and touch-up.
Yes, and accurate record keeping, using the right materials and qualified people, maintaining the basic finish systems.
Keeping drain holes clear, that seems simple but critical.
Hugely important. Draining fuel cell sumps daily to get water out. Daily wipe downs of critical areas. Sealing the aircraft against water entry in bad weather. Proper ventilation when parked. Replacing damaged gaskets and sealants promptly. Using protective covers when parked. It all adds up.
It really makes the point that skipping this stuff just means bigger, more expensive, potentially dangerous problems later.
It's an investment, pure and simple. An investment in safety and longevity.
Okay, so prevention is key, but stuff still happens. Inspection is the next line of defense. And it's not just during major checks, right? It's continuous.
Exactly. Corrosion inspection needs to be a daily mindset for technicians. The general process starts with thorough cleaning. You have to see the surface clearly. Then a good visual check, using flashlights, mirrors, maybe a magnifying glass, 510x, for suspicious spots. Then you do a detailed inspection of any areas you're concerned about. And don't underestimate touch feeling for roughness or blistering under paint. Mirrors, optical micrometers, depth gauges for pits, all useful tools.
And sometimes you have to remove panels or equipment to really get a look.
Often, yes. Access is key. Removing panels, fairings, equipment, sometimes even sealant or paint is necessary. Borescopes, fiber optics are essential for getting into those really tight internal spaces.
The chapter mentioned NDI non-destructive inspection briefly too, things like dye penetrant, eddy current.
Right. Those are powerful tools for finding hidden damage, including corrosion, cracks, etc. But they absolutely require properly qualified and certified personnel and correctly calibrated equipment. It's not something you just dabble in. And worth noting again, amphibians and seaplanes need daily inspection and cleaning treatment due to that constant water exposure, especially salt water.
Okay, so where should people be looking extra closely? The chapter listed a bunch of known trouble spots.
Yeah, the corrosion-prone areas. Exhaust trails are a big one. Corrosive deposits get trapped in gaps, seams, hinges downstream of the exhaust. Rivet heads, lap joints are common spots there. Battery compartments and vent areas, those fumes are nasty and hard to contain. Bilge areas, the low points where water, hydraulic fluid, dirt all collect. Oil leaks can hide water there too.
Lavatories, galleys, makes sense. Spilled food, waste, moisture. And wheel wells and landing gear, they just get blasted with everything from the runway.
Absolutely. Mud, water, salt, gravel. Plus they're complex shapes, hard to paint perfectly, hard to keep clean. Magnesium wheels need careful checks, especially around bolt heads and lugs. Exposed tubing, B-nuts, ferrules under clamps, electrical connectors, switches, axle interiors, struts, links. Lots of crevices and hardware.
Water entrapment areas anywhere on the aircraft sound critical. Keep those drains clear.
Crucial. Daily check of low-point drains. Engine frontal areas and cooling air vents get eroded by airborne particles, removing the protective finish. Unpainted cooler cores, cylinder fins, and salt ingestion is a huge issue in marine environments. Maintaining protection is vital, especially on seaplane engines. Wing flap and spoiler recesses, dirt and water collect there when they're retracted, so you need to inspect them when deployed.
What about the main skin? Seems more exposed, maybe easier to see.
Generally, yes, but there are still issues. Magnesium skins need that original finish kept pristine and proper insulation from other metals. Touch-ups are never quite as good. Check edges around fasteners, any damaged paint. Piano-type hinges are notorious to similar metals. They trap dirt and salt. Need regular lubrication with water-displacing lube and actuation. Spot-welded skins can corrode between the layers if moisture gets in. Look for bulging or corrosion products squeezing out. Sealing entry points is key.
Okay. What else?
Electronic and electrical compartments, similar conditions to engine areas, maybe less severe, but sensitive components. Helicopter rotor heads and gearboxes exposed, complex, often dissimilar metals. And control cables, check externally by cleaning sections. Check internally under tension. Light rust can sometimes be removed carefully and preservative reapplied.
So let's say you find corrosion. Now what? The chapter outlines a process. Clean, strip, remove, neutralize, restore protection, repaint. Unless it's too bad, then replacement.
That's the basic workflow, yes. Correcting the damage before it exceeds limits. The two main removal methods are mechanical and chemical, depending on the metal and how bad it is.
For cleaning and stripping paint, preliminary cleaning first to see the extent, and try not to strip more than needed.
Exactly. Minimize stripping if possible. Use the least aggressive method that works. Water-based, non-toxic cleaners are preferred. Dry cleaning solvent for oil grease. Emulsion cleaners for heavy preservatives. General-purpose strippers are common. Always think safety. Outdoors or good ventilation for chemical stripping. Protect rubber, plastics, fabrics. Be careful near sealants. Mask openings. Wear your PPE gloves, apron, goggles. Apply the stripper, let it dwell, scrub if needed, maybe reapply. Use non-metallic scrapers or pads, then wash and rinse like crazy. Dispose of the waste properly.
And if the removal leaves dents or pits, they need to be blended, fared smooth.
Yes, very important, especially in structural areas. Rough edges or pits act as stress risers. You need to blend them smoothly. Dish outs should be gradual, elliptical, often with a 20-to-1 length-to-depth ratio as a guideline. In critical areas, all pitting needs to be blended out. In non-critical areas treated by blasting, some minor pits might be acceptable without blending, but always check the manual. If pits are close together, blend the whole area between them. Remove steel fasteners before blending aluminum, and make absolutely sure all corroding products are gone.
Okay, let's talk specifics. Ferrous metals rust. The chapter says rust itself promotes more rust.
It does. It's porous, holds moisture right against the steel. Not protective at all. So all rust must be removed. Even small amounts on stressed steel are dangerous. Remove it and assess the damage ASAP.
How do you get it off, mechanically?
Mechanical methods include abrasive papers, compounds, wire brushing, maybe steel wool, except on highly stressed parts. The risk is leaving residue in pits. Non-woven abrasive pads, used with light oil, are often very effective. Chemical removal is also an option. Non-caustic rust removers are preferred as they don't etch the base metal. Ideally, remove the part for treatment to ensure full rinsing. Caustic removers need careful masking and dimensional checks afterwards. There are also chemical treatments that convert rust to a passive phosphate layer, but generally not for assembled aircraft due to rinsing issues. And chemical inhibitors are usually a bad idea on installed parts due to entrapment risks.
What about highly stressed steel parts? Any rust seems critical there.
Absolutely critical. Removal must be very careful, using only mild abrasives rouge, fine aluminum oxide, fine buffing compounds, non-woven pads. Don't overheat the part during duffing. Reprotect immediately with paint. Chemical removers are generally forbidden without specific engineering approval due to the risk of hydrogen embrittlement, making the steel brittle.
Right.
Now, aluminum. The most common material, but it has its issues, right? Forms that oxide film, but vulnerable to galvanic corrosion.
Exactly. And the oxide film is good, but easily damaged. And aluminum is quite active, so it loses out in galvanic couples with many metals. Prone to pitting, intergranular, stress, corrosion, cracking, depending on the alloy and conditions. Its corrosion products are typically white and quite voluminous. Early signs are etching, pitting, roughness. A thin, uniform oxide layer is okay, even protective. But attack accelerates with salts. Serious forms are penetrating pits, stress, corrosion, cracking, and intergranular, especially in improperly heat-treated alloys. But often, you can treat it in place.
How do you treat unpainted aluminum, like Alclad, to keep it polished?
Basically, yes. Maintain that polished condition. Avoid mechanically removing the pure aluminum Alclad layer if possible. The sequence is usually mild cleaner, hand polish with fine abrasives, or metal polish, but not on anodized surfaces. Then an inhibitive treatment like a chromate solution. Dwell, rinse, dry, followed by a waterproof wax coating.
And for surfaces that will be painted, you could be a bit more aggressive. Clean thoroughly. Strip old paint. Treat corroded spots, often with a dilute chromic or sulfuric acid solution. Scrub, dwell briefly, flush wipe clean. Dry it well, then get the proper protective paint system back on immediately. Same day, ideally.
What about anodized surfaces? That finish is deliberately created for protection.
Right, so you want to preserve as much of it as possible. No steel wool, steel brushes, harsh abrasives.
Yeah.
Use non-woven pads, aluminum wool gently, fiber brushes. Treat the corroded area similarly to other aluminum, and inhibitive chemical treatments like chromic acid can help restore some protection to the damaged film.
And if you find that nasty intergranular corrosion,
that usually requires more aggressive mechanical removal of all the corroded and delaminated material to see how deep the damage goes and assess the remaining strength. There are often specific limits in the repair manuals for how much material can be removed. If it exceeds those, you'll need a structural engineer, a BER, to evaluate it.
magnesium sounds like the problem child. Most chemically active, hardest to protect.
That sums it up pretty well. Very active. If the coating gets damaged, it corrodes fast, producing lots of white, powdery, or flaky stuff, sometimes even whiskers. Prompt, complete correction is essential. Remove the corrosion, chemically treat the surface, reapply the full protective coating system.
How do you treat it, say, on a sheet metal part?
Often occurs at edges, under washers, damaged spots. If possible, remove the part for thorough treatment. Loosen washers to treat underneath. Mechanically remove as much as possible, but only with stiff non-metallic brushes or non-woven pads. Absolutely no steel or aluminum tools or wool cross-contamination is a huge risk. Then, clean and strip paint. Apply a chromic acid solution with added sulfuric acid, work it into pits, let it dwell, 520 microns, wipe off excess carefully, don't let it dry, then restore the original paint system ASAP.
What about magnesium castings, like engine cases?
They're more porous, so corrosion can penetrate faster and deeper. Treat similarly, but promptness is even more critical. Saltwater can eat through a casting literally overnight. If possible, separate mating surfaces for treatment. If a lot of material needs removing, you'll definitely need to consult the manufacturer's limits and repair manuals.
Titanium. Generally good, but not totally immune.
Correct.
Yeah.
Very corrosion resistant, but salts and metal impurities, especially at high temps, can cause issues. Key rules. No steel wool, iron scrapers, steel brushes. Clean by hand polishing with aluminum polish or mild abrasive using only fiber brushes. Follow with a sodium dichromate solution. Wipe off excess. No water rinse needed.
And protecting dissimilar metal contacts, we keep coming back to this, usually involves a barrier.
Yes. You have to prevent direct contact in the presence of moisture, especially salt water, to stop galvanic corrosion. The manuals will specify required separators for different metal pairs, primers, special tapes, washers, grease, sealant. Generally, for non-magnesium contacts, at least 2 coats of zinc chromate or epoxy primer on the faying surfaces, plus the normal primer. For contacts involving magnesium, it's 2 primer coats on each surface, plus a layer of .003 vinyl tape applied smoothly. If tape interferes or temps are too high, over 250 Gers MN tape, use at least 3 primer coats instead of tape.
And finally, corrosion limits. Any corrosion is damage, right, but classified.
Exactly. It's categorized.
Yeah.
Negligible, repairable by patching, repairable by insertion, or requires replacement. Even negligible needs proper cleaning, treatment, and repainting. Repairs must follow the structural repair manual. If damage exceeds limits, the part must be replaced. No hook cuts.
Okay, shifting gears slightly. The chapter also covers some background on the processes and materials used in corrosion control, which helps understand the maintenance side, like metal finishing.
Right. Manufacturers apply finishes mainly for corrosion resistance, but also for wear resistance or as a base for paint. You often can't fully replicate these original factory finishes in the field, but understanding them helps with proper maintenance and partial restoration. Surface preparation is key for any finish. For steel, that means removing all dirt, oil, grease, oxides, moisture. It can be mechanical wire brush, steel wool, sandblasting, but chemical cleaning is often preferred as it doesn't remove base metal. Pickling in acid removes scale before plating. Electrocleaning uses an alkaline solution and current.
And for aluminum or magnesium, similar prep.
Similar methods, yeah. But you have to be careful with blast cleaning on thin aluminum, especially alclad, and never use steel grit on aluminum or stainless steels. Polishing and buffing are also important steps sometimes, especially before plating.
Then there are chemical treatments. Anodizing for aluminum.
Yes, anodizing creates a much thicker, denser protective aluminum oxide film using an electrolytic process. Great corrosion resistance, good paint base. But it's relatively soft, easily scratched. So, again, careful cleaning aluminum wool, non-woven pads, fiber brushes only, no steel wool or harsh abrasives. Also, the anodic coating is a poor electrical conductor, so it has to be removed where electrical bonding is needed.
And alodizing. Sounds similar.
It's a simpler, non-electrolytic chemical conversion coating process for aluminum. Provides corrosion resistance and a paint base. It's largely replaced anodizing for many applications because it's faster and simpler. Involves cleaning, rinsing, applying the alodine or bonderite solution, rinsing again, and a final rinse that leaves the surface slightly acidic.
What about chemical treatments done in the field during maintenance?
Right, you often can't redo the original anodize or alodize. So when you treat corrosion, you use chemical surface treatments or inhibitors before repainting. Always check the SDS for hazards. Some of these chemicals react violently with things like paint thinners. A common one is a chromic acid inhibitor solution, sometimes with sulfuric acid added. Effective on bare or corroded aluminum and magnesium, helps restore the oxide film. Needs painting ASP afterwards. Chromium trioxide is a strong oxidizer. Handle with care. Sodium dichromate solution is a less aggressive option for aluminum, and there are commercial activated chromate mixtures approved for treating damaged aluminum again. Handle carefully, rinse cloths well to prevent fire risk when they dry.
And paint itself is a major protective layer.
The primary barrier, really. Common types are catalyzed polyurethane enamels, waterborne polyurethanes, increasingly used due to environmental regulations, and two-part epoxy paints, plus specialized coatings like dope for fabric, high-vis paints, rain erosion coatings, baked enamel on wheels, etc.
Which brings us back to cleaning. Hugely important, the chapter stresses.
Absolutely critical for accurate inspections, preventing wear, reducing weight and drag, general safety. Always follow the aircraft maintenance manual for approved cleaning agents. Agents vary: solvents, emulsion cleaners, soaps, synthetic detergents, usually classified as light duty or heavy duty. Use the mildest effective cleaner, preferably non-toxic, non-flammable. Needs to rinse easily, and be careful with the alkaline cleaners getting trapped in joints.
How about exterior cleaning methods? Wet wash, dry wash.
Wet wash uses water, usually with alkaline or emulsion cleaners sprayed or mopped on, then rinsed off. Good for oil, grease, general dirt. Dry wash uses minimal liquid, applied and wiped off with cloths or mops. Good for light dust or film when liquids aren't desirable. Polishing restores luster and removes light oxidation using various abrasive polishes, and lots of precautions for exterior washing. Wash in the shade if possible, cover openings like pitot ports. Be gentle on flat finish paint areas. Flush plastics with water before washing. Use soap and water by hand. Rinse well, dry carefully with chamois or soft cloths. Don't rub dry plastics. Avoid harsh solvents on plastics. Wash tires with mild soap. Lubricate grease fittings after washing.
Interior cleaning sounds just as important, maybe even trickier with hidden areas.
It can be. Corrosion can really take hold in hard-to-reach spots, and metal debris filings, rivet shavings left during structural work is a big hazard. Mixed with moisture and dissimilar metals. Perfect recipe for corrosion. Clean up meticulously, use drop cloths, vacuum cleaners. And ventilation is a huge concern inside cabins when using flammable cleaners. Vapors can build up. Find an ignition source. Use non-flammable agents whenever possible.
What kinds of non-flammable options are there for interiors?
Detergents and soaps. But be careful they don't leach out fire retardant treatments or harm aluminum. Alkaline cleaners are stronger but can damage some materials. Mild acid solutions for certain stains, again with caution. Deodorizers, disinfectants, check the propellant isn't flammable. Dry cleaning solvents like perchloroethylene, but these have toxicity and environmental concerns.
And flammable cleaners, sometimes necessary.
Sometimes, but with extreme caution. High flashpoint solvents like Stoddard solvent are preferred over low flashpoint ones like acetone or gasoline, which should generally be avoided. Mixed liquids are risky unless you know exactly what's in them. Always use approved labeled safety containers.
Fire prevention is paramount then.
Absolutely. Maximum ventilation. Shut down all ignition sources. Use only approved explosion-proof electrical equipment. Don't operate switches during cleaning. Post warning signs. Have proper fire extinguishers readily available, minimum 20B rated portable extinguishers at entrances, maybe booster hoses or other agents. Note that standard ABC dry chem extinguishers can be corrosive to aluminum. Work outdoors if possible, or in a hangar with proper fire protection systems.
What about cleaning the power plant itself?
Vital. Grease and dirt act as insulators on air-cooled engines. Hide cracks. Open or remove cowlings. Wash down carefully with kerosene or solvent spray, maybe a soft brush. Propellers get cleaned with soap and water or approved solvents generally. No caustics, scrapers, or power buffers that could scratch. Pits on prop leading edges from impacts are bad. They can grow due to corrosion and fatigue. Steel props are tougher but still need care. Maybe oiling after flights helps. Clean hubs carefully. You can use metal polish for shine, but remove all traces, clean, and oil afterwards. Rinse everything thoroughly. Lubricate moving parts after cleaning per the manual.
Let's quickly run through some common solvent types mentioned.
Okay. Generally want flash points above 105 degrees of AF for safety. Chlorinated solvents are non-flammable but toxic. Avoid carbon tet. Always check the SDS. MEK and acetone are very active but flammable and harmful use with precautions, often replaced by safer options now. Dry cleaning solvent, Stoddard is common. Flash point just over 105 degrees of AF, good for grease but leaves residue. Aliphatic naphtha for wipe downs, safer than aromatic naphtha, which is toxic and attacks rubber plastics. Safety solvent, trichloroethane, was common, less flammable, but still a chlorinated solvent with risks. Kerosene is used, often mixed with emulsion cleaners, but leaves a film that needs removing.
Special cleaner for oxygen systems.
Yes, anhydrous ethyl or isopropyl alcohol, only for accessible parts like masks and lines. Never put fluids in tanks or regulators. No oily cleaners allowed. Follow manufacturer instructions strictly.
Emulsion cleaners. Mixture of solvent and water.
Right. Good for heavy grease, oil, tar. Usually safe on paint if used correctly. Water emulsion types are milder. Solvent emulsions can be non-phenolic, safer on paint, or phenolic, stronger, but can soften paint. Need care with nonmetallics.
Soaps and detergents for lighter cleaning.
Yes, mild cleaning. Standard aircraft surface cleaners exist, like Melissa 5410. Non-ionic detergents are versatile. Be gentle scrubbing flat finishes.
Mechanical cleaning materials, abrasive.
Use with care. Mild options include non-woven abrasive pads, various grades, great for light corrosion, clean, don't cross-contaminate metals. Powdered pumice, impregnated cotton wadding for polishing, aluminum metal polish for unpainted alclad only, aluminum wool, less preferred now than nylon pads, rubbing compound for light oxidation, abrasive papers, use aluminum oxide, 300 grit or finer, avoid silicon carbide, carborundum, grains embed, absolutely avoid emery paper or crocus cloth on aluminum or magnesium embedded iron oxide causes corrosion.
And chemical cleaners again, but specifically for use on the assembled aircraft. Sounds risky.
Very risky due to entrapment. Must be relatively neutral, easily rinsed. Residues can cause blistering later. Phosphoric citric acid mixes are used for aluminum sometimes. Wear protection, neutralize spills. Baking soda is used to neutralize acid spills, like from batteries.
Wow. Okay, that covers an incredible amount of detail. This deep dive into just one chapter on cleaning and corrosion really drives home how complex and critical this is. It's so much more than just washing a plane.
It really is. It's a constant science-based effort against the natural tendency of materials to degrade. Understanding the different types of corrosion, what causes them, how to find them, and how to correctly treat them is absolutely fundamental for aircraft maintenance technicians.
And it hammers home that even seemingly minor corrosion, if ignored, can have truly major consequences for safety and the aircraft's lifespan.
No doubt about it.
You know, thinking about the sheer level of detail and vigilance required just for this one aspect, corrosion control, it does make you wonder, what other critical systems in our lives, what other technologies rely on this kind of meticulous, often invisible, ongoing maintenance to keep us safe and keep things running reliably every day? Things we probably just take for granted.
That's a really interesting thought. There's a lot going on behind the scenes to keep our modern world functioning.
Definitely something to ponder. Well, thank you so much for taking this deep dive with me today. This was incredibly informative.
My pleasure. It's a vital topic.